Okay, so I've said this a few times during this unit. Hopefully you recall this. If not, I'll say it again. There are 4 main sections to this unit. We need to learn about 4 function types. So we've just finished a week on polynomials. And essentially we're going to do 1 week for each type. So polynomials are things like linears, cubics, quadratics. And hopefully you're getting fairly good at being able to graph those, know their properties. Next week, I want to really focus on the next type, which is exponential functions. The week after that, we're going to do logarithmic functions. And the week after that, we're going to do sinusoidal functions. And really, they all kind of fit the same sort of pattern. I'm going to start with a little bit of like an intro lesson, trying to take what you already know and hopefully build on it. Then we'll talk about what the picture of the graph looks like, the main properties of it. And you know how we've been working on that whole list 1, list 2, where you do regression stuff? We're also still going to do that for different functions as well. So the unit is kind of nice in a way where once you get the hang of it, it's very repetitive, and all you just do is add just a new type of function to it. So today's topic is basically just a review lesson before next week. I just want to review for you guys what exponents are, because you need to have a decent knowledge of how exponents work before we can actually graph these properly. So here I found a slide on the internet somewhere that just reminds you of just some of the terminology we'll use. The terminology is base and exponent. Maybe you use the word index or power. We're going to even ask you guys to try to talk about like the degree of a function. You know what I mean? Like x to the power of 2 is a degree of 2. X to the power of 3 is a degree of 3, right? So index, power, we actually use that already. The base then is like the big number that goes in the bottom. Right? So if I tell you 6 to the 3, it means write a 6 3 times. Is that review? I mean, I feel like, I don't know, when did you learn that for the first time? Grade 8, maybe? 1? So, okay. Here's another review slide. So, reminder, we're doing functions. Functions are equations. So, here's some of the things that we might be able to graph, like this guy right here. I know it's written in an odd order, but it's a 5, then a 4, then a 3. There's no 2, there's a 1, there's a 0. This is a quintic. Quint, right? 5 would be quint. Here's linear. Here's quadratic. This one right here, I stole the slide out of my Math-1 notes. We don't actually graph anything that's a fraction, but we did do an entire unit on the algebra behind fractions. So hopefully you recognize, you know, the fraction concept from the first year, but we don't actually graph them. So, okay, here's a review slide just talking about, again, how exponents work. They're similar in that they both have exponents and powers. What sort of graph is this? This is quadratic, right? Well, just to remind you what this actually means at like at the like below surface level here, x squared means x next to x times x. 5x though means x plus x plus x plus x plus x. 5 times. We've added x to itself 5 times. That's what 5x means. Minus 6. Could you guys do that same sort of task on this one right here? Let's do it as a group. What would negative 3x to the 6 mean? Well, it would mean negative 3, and then there's 6 x's, right? Do they need to be added to each other or multiplied by each other? Yeah, so you'd have to go like x, 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 x. That's what negative 3x to the 6 actually means. What does minus 3x squared mean? Well, it means you have like minus xx, minus xx, minus xx. In a way, you have 3 of them. I mean, if you wanted to, you could take all of this stuff right here and say that you have negative 3 xx's. But that's what it means, right? The 3 means you have 3 of them all subtracted from each other. Well, how does it apply to 6x? Well, it means that you could write it as 6x, I guess. Or you could also write it as, let's change the way I do that though. Or you could write it as x plus x plus x plus x. Pardon me. That's what 6x means. 6x means add x 6 times. X to the 6th, though, means times x 6 times. You see the subtle difference between the two there? And I guess there's like a -7 still on the end of this. Good? Sure. You're either good or you're disinterested, one of the two. All right. Here's a picture I found, just reminding you again what x means. That means x to the 4. What we're going to do today now is we're going to migrate into this notation. This is called an exponential function, where rather than having the base, the big number below be x, and the exponent be a number, we're now going to switch it around and make it so that the base is the number, and the exponent is where x goes. So you guys see how it's kind of similar in a way? It still involves a number underneath, a base number, and an exponent, but the variable now is going to become our exponent. This notation here means 2 times by 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 2.
Just forever.
Forever. Thank you. Someone finally stopped me there.
I
Right?
thought you were just talking about that.
But I was doing it to make a point, though, right? 2 to the power of x means keep timesing 2 over and over again, and you don't get to stop. Does that make sense? If I tell you what x is, then you know that you got to times it like 5 times in a row or 7 times in a row. But if I don't tell you what x is, you got to keep doing it infinitely. Right? So what does this mean right here? Well, this one right here is the kind of function that we're going to focus on. Again, on Monday, we're going to spend more time on it, but this is kind of like my pre-lesson to kind of just talk about some of the properties. This means 2 gets timesed infinitely. But before you do that, though, you times it by 5. So you start with a 5, then you times 2 by 2 by 2 by 2 by 2 by 2. I'll not do this time, right? And then this -6 means after you're finally allowed to stop, whenever it is you're allowed to stop, then you get to subtract 6. The common mistake that kids will make, though, is they'll look at this example and they'll say 5 times 2 is 10. And so this means 10 times 10 times 10 times 10. But according to BEDMAS, that's not how this works, because the bracket right here means that only the 2 gets repeated over and over again. Does that make sense? Okay. My goal today is to help us just to refresh your memory about some of the laws of exponents. So here's 2 laws that they're very grainy, but maybe you've seen these before. Let me do like an example that maybe fits better here. If I gave you x to the power of 2 times by x to the power of 3, the rule is x squared really means x times x. X to the 3 really means x times x times x. How many x's do you have? 5. So take your 2 and your 3 and add them together. Does that make sense? If I were to give you 2 to the x, then, times by 2 to the y, the answer then would be 2 to the x plus y. I don't know how many 2's I get here. 7. I don't know how many 2's I get here. 4. But I do know that whatever these numbers end up having to be, whenever we decide what they are, we have to add them together. Does that make sense? Similar rules apply with dividing. If I give you x to the power of 7 over x to the power of 2, hopefully what you can interpret is there are 7 x's all right next to each other here, and then there's 2 on the bottom. Well, what happens? Well, they cancel, right? So 7 minus 2 means that you're left with x to the 5. Well, similarly, if I were to give you 4 to the power of x divided by 4 to the power of z, you would say this is 4 to the power of x minus z. That makes sense? What if I gave you 4 to the power of x divided by 3 to the power of z? Does that same rule apply? No, it does not. You have to have the same base. Okay, so if you don't have the same base, it's no good. But if you do have the same base, subtract the exponents if you divide. Adding means multiply. So, here's a couple of just really simple examples then. If you have n to the 3 and n to the 3, how many n's do you have? Yeah, just add them together. m to the 2 and m to the 7? Yeah, you have m to the 9. Add them together. M to the minus 4 and m to the 3. Well, still add them together, right? It just means you have m to the minus 1. That's all. Same logic applies. What about this last one? Yeah, it's like the exact same thing you started with. You cannot do anything more. It's like this is as good as it gets, right? You can't add n's and m's just like you can't do a's and b's or apples and oranges, right? Has to be the same letter. Is this mostly review at this point here? Because that's what it's supposed to be. Hopefully this is just re-jogging your memories about some rules of exponents that at one point in your life you've learned. So here's another couple of rules. If you ever have exponents and you put like one of them in brackets to a power of another one, then you can multiply them. So as an example, if I gave you 3 to the x all to the power of 8, this is now equal to 3 to the 8x. Just take the 8 and the x and times them together. Or if I gave you 4 to the z all to the power of smiley face, well, that's the same thing as 4z smiley face. Just times them together. Or if I gave you x to the 2 to the power of 3, it's now x to the 6. Okay? Okay. If you ever have two things inside a bracket and then you give an exponent, it's not foiling. This is the most common mistake kids will make. They'll see like a or xy squared, and they'll think that they have to go like x squared plus xy plus xy plus y squared, and they'll like try to foil it. Does that make sense? But foiling only applies when there's like an add or subtract sign in between. So what I just did there was very much wrong. All you do in this case here is the exponent applies to the first one and the second one individually. So if I told you that you had 2x all to the power of y, this could be written as 2 to the power of y and x to the power of y. And the same thing applies to dividing, but I think we can probably move past that. So let's do another set of examples here. What does ab to the 3 really mean? Well, it means you have a and then 3 b's. Ab. You even laughed. Thank you for the pity laugh. Appreciate it. Can you really do much with this first one here? No, not really. What about this one over here? What does a, b in brackets to the 3 really mean? It means you have a to the 3, and you also have b to the 3. So if you really wanted to write that out, it's ab. There you go. Nobody laughs. Thank you. Okay, let's try this next bottom one down here. Well, the top of this fraction means that you have x to the 3, because like the 3 applies to the x, right? But what happens when this 3 applies to the 2? How many y's do you have? Do you have 5 or 6? Well, really, this means that you have y squared next to another y squared next to another y squared.
So what's yours for y?
Yeah, so it is 6. You're right. Y to the 6. Over x squared. You could cancel the x's, right? If you have 3 of them on the top and 2 on the bottom, yeah. So there's just 1 left on top. So the best answer for this is x to the 1, y to the 6. Or if you really had to write it out, which we probably wouldn't do, it would mean that. That's what it means when you're done. 1x times by 6 y's. Okay, one last one here. Well, this 2 right here kind of applies to both of these guys. So it means you have an x squared. If you have 2y to the 4s, you have y to the 8. Right? What about the bottom? Well, you have 3 x's and you have 3 y's. By the way, this x right here was meant to be like a times sign. So if we times that by yx to the 5, it's almost like you can just kind of continue that fraction going. How many y's do we have on the top total now?
9.
Yeah, 9, right? 8 from this guy. 1 more over there means I actually have 9 y's on the top. How many x's do I have on the top?
7.
7's right, yeah. 2 right here. 5 more right here. You have 7 total. On the bottom, we still have 3 and 3. I should be able to reduce it a little bit, right? So let's see. We got 7 x's on top, 3 on the bottom. So 4 x's. And 9 and 3 is 6. Yeah, subtract. The biggest thing I want you guys to work on is know when to use your multiply and your add rules. It's almost kind of like terms and combs in a way, where multiply is in a certain scenario and add is in a certain scenario. You have to know when you're adding and when you're multiplying, when you're subtracting, when you're dividing. Ideally, this should be a review of grade, I don't know, 7, 8, 9, 10-ish type there. So I just want to make sure you have a firm basis of this before we do graphs. So everyone feel fairly comfortable on that? Cool. Okay, here's a slide with one more thing on this, and this one's a little bit more obscure. There's 2 other rules that you guys should definitely be aware of, and it involves exponents that are fractions and exponents that are negatives. Fraction exponents are actually square roots. If I give you n to the power of a half, it's the square root. If I give you n to the power of a third, it's a cubed root. Have you guys seen that before? Do you remember this at all?
Yes.
Okay, I know I've done this even in this course because I pulled this slide from one of our first units. Negative exponents also have their own rule. If you have a negative 1, it's 1 over n. If you have a negative 2, it's 1 over n, but the n is to the power of the 2. So it's always 1 over something, and whatever the exponent is, that becomes the exponent on the bottom. So a negative exponent just means that you have variables on the bottom of a fraction. Sound good? Okay. That's the review section. I want to do, I think, 1 or 2 slides here. Yeah. There's just a summary slide then with all the rules I need you to know. I just want to do a real basic start now of what an exponential function is going to look like. So I don't want to go into great detail. I just want to do a couple of tables of values and then we'll call it a day. So I want to just talk about what this graph might look like. Just doing a table of values to start with. So what does 10 to the x mean? 10 times 10 times 10 times 10 times 10, and you're not allowed to stop saying that until I tell you what x is. Okay, you can stop. Okay, so if we do a table of values now, really, the answer depends on what x is. So let's start with a good old value of x being 1. Well, then the way you'd say this is 10, right? You'd go 10 to the power of 1, so you get 110. So that'd be 10. Well, what happened if x was 2?
20.
Not 20. It would be 10 times 10. Yeah, this is why I want to do the review lesson today, because you can't get your add and your multiply screwed up. Yeah. What would 10 to the 3 be? 10 times 10 times 10, which is not 30. What is it? That's 1,000. What's happening every single time I add another? That's a 0, right? No. If I did 4, I think we'll just stop at 4 at this point here. It would be 10 times 10 times 10 times 10. That's actually 10,000. What happens in exponential graphs is they go very high very fast. They basically they take off. Sometimes you'll hear about things growing exponentially. This is a good example. If something grows exponentially, it is. I mean, day 1 you had $10. Day 2 you had $100. Day 4 you have $10,000. I would love to invest in that bank account, right? That's a good investment. It's not good if it's the amount of mosquitoes in my backyard, right? Okay, I should talk about a few more numbers though. I've done the positive numbers, but I haven't done a few of the other common numbers, like for example 0. Yeah, it's just 1, yeah. I skipped over this slide, but I should go back to one here. If you ever get a variable to the power of 0, it's been defined as the number 1. Basically, it means you have no a's. Well, it means that you have here's a whole bunch of a's. In a way, it's like you have 1 times a whole bunch of times. But then I'm telling you actually have none of those a's. You don't have this a, you don't have this a. Well, what's left? The number 1 is left over, technically. Some people think it should be 0, but it's not. So just memorize that rule. I'd also like to talk a little bit about what happens to negative numbers, like -1 and -2. Well, what does a negative exponent mean? 10 to the -1 means 1 over 10 to the 1, which is a tenth. A tenth is 0.1. If it was a -2, it would be 10 to the -2. Negative exponents mean write 1 over top of what you have. So it's 1 over top of 10 squared. 10 squared is 100. So yeah, you guys are ahead of me here. It's 0.01. As I make my exponents become more and more negative, it actually makes the number have more and more zeros in front of the number, which is actually where that whole exponential notation comes from. Right? Like if you have 10 to the power of -4, it means that you're moving the decimal place over 4 times, right? So that makes sense so far? Okay. I want to focus on the graphs another day, but just so you're aware of what the graph would look like. If I plotted a few points, a few of the key points would be here. The point at the y-intercept would actually be at 1. 0 goes with 1. 1 would give you 10. 10 would give you 100. I don't even think I could draw 100 on this graph because it would be like way the heck up there. So like this graph basically shoots up like a rocket ship. Now, even though I don't see any graph over here though, even though I don't see any graph, does the function still exist? Yeah, sure. It's just super way high up. However, in the negatives where it gets interesting. -1 is 0.1. Then it's 0.01. Then it's 0.001. Basically what happens is this graph gets very, very tiny. Almost 0. It'll never actually get to 0.
Ken Bottle. Sarah Beatty, please come down to the office. Jessica Wadsworth, come down to the office.
Like even if you did -10, it's basically just going to be 0 point and then a whole bunch of zeros in front. So the graph will actually never get into the negatives. Let me say that one more time. This graph will never get into the negatives. It is not physically possible for an exponential graph like this to be in the negatives, because even if you pick a negative exponent, all it does is it makes it a very, very small number. So on Monday, when we talk more about properties, one of the things I'm going to point out is that your range is always something like y is greater than 0. Because it can never be negative. Okay, let's try another one here. We're going to do 2, then bracket 5 to the x. What would this look like in a table of values? Well, let's start with a good old 1 for x. It would be 2 times 5, so it'd be 10. Because you're doing 5 once, right? Well, what if x is 2? Well, it would be 2 times 5 times 5. Not 20, though. Yeah, good. Yeah, you made a really common mistake. What you end up doing, some people do, is they'll put the 2 and the 5 together, they'll make it a 10, and then they'll double the 10. But that's not how it works. You only double the 5 and then times by 2. So like for 3, you do 3 5s with 1 2. So like 5 times 5 times 5 is 125. Good, yeah. It's still taking off like a rocket ship, right? Like this graph is getting very big, very fast. But that 2 in front, like you can start to see a pattern here, right? Every single number is going to have a single 2 in front followed by a certain number of 5s. That's 625 times by 2. $13.50? No, $12.50. I think that was $12.50. Anybody try it? 2 times 5, 4 times? 6,250?
Yeah, I got 12.
For this one here? Or are you on the one after?
I'm on 5.
That one, is this one 6,000?
250.
250? Anybody else try that one?
I got 6.
You got that? Okay, cool. Okay, we should also, however, talk about the other numbers that exist. So we can't just do positive numbers, as nice as those are. Because really, what's the point of doing 6, 7, and 8? Don't we know that this graph is just going to become very big, basically? So we should try 0. The cool thing about 0 is that you have 2 times by 5 0 times. Well, if you have literally no 5s, what do you have left? You have 2 left, yeah. Seems kind of odd, but 2 times 5 0 times. Doesn't mean it's 2 times 0, it just means you have 2 times by, well, you're not timesing 2 by anything because you have no 5 times it by, so it's just 2.
Kyle Blood, please come to the office. Kyle Blood.
Let's try -1 and -2, and I think that should be enough. So this will be 2, and you know, I might need to go off to the side for more room here. It'll be 2 times by 1 over 5. Does that make sense? The 2 actually stays out front, and then the 5 to the -1 makes it 1 over 5, which this is actually 2/5. It's a small number now. This would be 2 times 5 to the -2. Well, that's 2 times 1 over 5 squared. The negative exponent means put the 5 back on the bottom. Because it's -2, square it still. But this 2, the point I want to make, it still kind of stays out front. So what's 5 squared?
I got 25.
It's 25. So this should be a 2 over 25. What did you get as a decimal?
0.08.
0.08? Okay. This guy's going to be 0.4, it looks like. The same property is actually going to happen here. It is not possible for us to get back a negative number. Make sense? Because try as we might, if we make x be like -1,000,000, well, it just becomes 2 times 1 over 1,000,000. Well, then it's like 2 over 1,000,000. It's not negative. It's not even 0, actually. 0 is also physically impossible to achieve on a graph like this. And so, like I said, on Monday, we'll focus more on what the graphs look like. But a graph of this looks something like this. The graph takes off very fast in this direction here, but it gets very, very small and very close to 0. But the whole bottom half of this graph, there is never anything down there because there just physically cannot be. Now think about certain scenarios where this might apply. Exponential scenarios include things like, well, I mentioned like mosquitoes multiplying, right? Can you have a negative number of mosquitoes? You can start with 1 mosquito, have it double to 2, have it double to 4, have it double to 8. But I don't know that you could really ever have negative mosquitoes. You know what I mean? Ideally, your money in your bank account should increase exponentially. I'd like to have $100, have it turn into 200, then 400, then 800. That'd be lovely, right? Technically, you can go in the hole in real life, but you really shouldn't. You know what I mean? You really shouldn't have negative money sitting in a bank account. That's not a good idea. That's not a good idea, at least. So, does this make sense so far? Okay. Let me just do one more. Can I just? I'll skip to this one with the 8 and the 1/4. I'll skip the one between it. We'll end with this one. What's different about this one and the one before it? That's kind of similar, I guess, but different than the previous ones.
Fractional bracket.
Yeah, the base is the word we use is the base is now a fraction. And that's also possible. You can have the base be a fraction. So I want to talk about what this would do. So we'll do the same thing, table of values. X and Y. Let's pick good old 1 to start with. Well, what happens here? Well, we take 8 and we times by a 4th. Once. 8 times by a 4th is kind of like 8 divided by 4. Cool. Okay. First number's 2. Then 2. If we make x be 2, it means we need 8. Then we need to times by a quarter. Then we need to times by a quarter again. Well, 8 divided by 4 is 2. And if you divide that by 4, I think it's a half.
0.5.
Yeah, 0.5. This is very strange. Exponential graphs are supposed to get bigger very fast. And as my x number increases here, it actually got smaller. Yeah, it's a decimal, right? Because what's happening here? You're taking 8, you're keeping a quarter of it, then you're keeping another quarter, then you're keeping another quarter. This would be like you have a certain amount of stuff, and then you get to keep a quarter of your stuff. But then you got to keep a quarter of that stuff. You got to keep a quarter of this stuff. Eventually, you don't have much stuff left because you keep losing most of what you have. Anybody have an answer for what this is?
0.5.
Cool. Would you guys agree, like, as we keep going here, this number should get smaller, actually? Right? But it'll never reach 0, right? Maybe this is a poor analogy, but let me give an example of one. You get divorced. You have to give half your stuff to your spouse. That makes sense? And then you go get married again. You get divorced. And you got to give half your stuff to that spouse. And then by the time you're on your 10th marriage, you've given half your stuff to the first wife, half of that stuff to the second wife, half of that stuff to the third wife. Do you still have stuff left? Well, technically. Hopefully you have a bed. But, I mean, at that point here, you've given most of your stuff away. Does that make sense? But you're never going to be in the negatives, hopefully. I mean, unless you go into debt. But you get the concept here, right? Because all you've been doing is just giving away half of your stuff over and over again, right? So same principle applies. This graph should never go below 0, though.
Well, I will do the negative.
Good, let's do those ones next then. So let's do 0 first, though.
It's 8.
0 is going to be 8, but let's just walk through why, just in case no one caught that. So this means you need 8 times by 1/4 0 times. Well, I'm telling you to take an 8 and then not times by anything, essentially. So it's 8. Just pretend that the 1/4 isn't even there. But you're right, this is going to go up. If you do -1, this means 8 times by 1/4 to the -1. Let me just go up top here and talk about what 1/4 to the -1 means. A negative exponent means take something from the top of the fraction, put it on the bottom. What if it's already on the bottom? Put it on the top. So this actually means 4/1 in a way. Yeah, that's a good way of putting it. So this is actually going to be 4 times by 8, which is going to be 32. Rather than the graph growing in the positive x values, it actually grows in the negative x values.
So what you're saying is you have negative lives, you get them.
Yes. That analogy does kind of work if you had like 5 wives and they all died but they had life insurance policies.
So
That's a very, very morbid example though. Yeah. Let's do -2 though. Just one more. So -2 means that you'd be doing 8 times by 1/4 to the -2. It means you'd have 8. You would then flip the 1/4 to going back to being regular 4, but then you'd square the 4. You still have to count for that 2 there. So you'd have to go 8 times 4 squared, whatever that is. 132 maybe? I don't know. 100 and something. 128?
28.
Yeah. So hopefully what you can see happening here, if we graphed this, the positive x values are actually getting very, very low. Never 0 though, and never negative. It's not possible to go in the hole in this particular example. You always just get half of what you have, but you're not losing it outright. However, over here, as you go backwards, this graph is actually very, very tall from up here. We actually have a name for this graph. We call this decay. where things are getting lost and decaying over time. There's a lot of overlap with this, by the way, in biology or in, like, say, physics. You guys already did Bio 30 if you took it, right?
Yeah.
Do you guys ever talk about, like, decaying organisms? Okay. So, like, decay basically, yeah. But it'll never reach zero or even get into the negatives. It's exactly like Half-Life. Yeah, if you've heard of Half-Life, it's the same concept.
Yeah.
You have to keep half of what you have. Okay, that's my review lesson. Hopefully most of this is, review. I have one last thought here. There's actually a page already in your math practice books that has a bunch of exponent practice. Yeah, we actually did it in the previous unit. So it actually wouldn't hurt to go back and try a couple of exponent examples. So here's my ask. Before you leave today, I was hoping for 10 examples of graphs that you draw. Can you throw on 5 exponents as well?
Like exponent.
Just off of the exponents page. So basically they're like how to add and multiply the exponents. Yeah, that should take no more than like 4 minutes, probably. Like they're pretty easy ones.
40 minutes?
4 minutes? So, can you guys finish up a journal entry for me with some practice in it? Ideally, your assignment should be due today. If it's not done today, that's fine, but the advice I'd give you, please don't procrastinate, because the longer you let things fall behind, the worse it gets, right? Like, it becomes an insurmountable pile. So if you have to hand it in late, I'm going to make you count it towards your grade, obviously. You can't omit it. But my best advice, though, would be to try to finish it Monday or Tuesday. Because just so you guys are aware, you're getting a new assignment next week, and a new one the week after that. So, like, it's going to compound. So, any questions? Big smile on his face, yeah.
Did you mark that last time?
I have a pile sitting right there that I'm... Yeah, it's again. I will. But no, I haven't yet. Okay, why don't you guys take a 5-minute break, and then you got 45 minutes to do stuff, whatever that stuff is. So, let me know how I can help otherwise.